Okay, so as mentioned, our lesson today is on sequences theory. Today's sequences in the general term. Okay, what happens all the time in this unit is that some people will look at this in the number sense and they'll either be able to get the question without any thought at all. Okay, if that's you, that's good. If it's not you, that's okay. I will use the formalized procedure to get things done to get going here. I'm going to pass, make it or square and first, and we'll pass back to Jake after the first one. So we're going to start with here, we're talking about sequences. A sequence is an ordered list of numbers. Each number is called a term. And this is what a lot of higher level math is this sort of defining patterns. Again, one of the reasons pi is so famous, not only related circles, but because it's a non-terminating, non-repeat, there's no pattern. People spend years, computers spend lots of their energy right now getting as exact as pi as possible to see if there's actual pattern. That would be like the ultimate mathematical result to find that pi is really equal to something, right? They haven't found it yet, right? But they're getting close. Or they getting closer and closer and closer and closer. Here we go. So this example one is going to say, find the next four terms in each sequence and explain why. Okay, we're going to start off with the nice ones. We're going to move up to more difficult. I have 5 here. A is 1, 2, 3, 4. I'm sure we'll handle that one today. B is, sorry, I apologize. Negative 52, negative 6, 18, negative 54. When we have 1, 3, 6, 10. We have. Oh. D is going to be, I'll throw it here. D is going to be 1, 1, 2, 3, 5, 8, 13. E is going to be 1, 4, 9, 16, and 4, 8, 15, 16. Okay, those are going to be our 6 sequences here. If you can find a pattern, I'll pause this here and give you guys a chance. 8. Your time to shine. 1, 2, 3, 4. What is the pattern, please? Add 1 each time. So it's obviously going to be 5, 6, 7, 8. Pattern add 1 each time. That should be probably the first pattern you learn as a student. Jake, you're up. 2, negative 6, 18, negative 54. You got it, Jake? Or no, we don't have it. That's okay. No? Yeah, go ahead.
162.
Yeah.
Negative 486.
Yeah.
1,458.
Yeah.
Negative 4,374. It
Okay.
multiplies by negative.
Excellent. Okay. So what she saw is, well, they go positive, negative, positive, negative, positive, negative. If you multiply by negative number, we're dividing. And then 2 to 6, 6 to 18, they all have to. This is a standard type of thing to do this. All right, now for another tricky one. Here. Joe, go ahead.
So the next one will be 15, 21, 28, 36.
Right, 15, go ahead, 21.
28, 36.
Okay, so what happened in this one? Yeah, so if you take a look here, this is going to be +2, +3, +4, +5, +6, +7. That's also quadratic. We're not going to talk about that right now. The second difference would be the same if you're looking at it that way, but that's easy. Are we starting to see what's happening here in this unit here? Express, you'd say increasing by one more each time is what you would want to say. Increasing by one more each time. And what's going to happen is that we're eventually going to learn how to make an equation of this. Okay, right? So we'll actually formally do the equation part for how to do that. All right, another volunteer that hasn't raised their hands yet. Number D, go ahead. D is 21, 34. You said, what was it, 21? Yeah? Can anyone else see what happened there? Sorry, you're out. Can anyone else see what happened there? Amy, what happened there? Yeah. See, this is the magic one. I love this. 1 + 1 is 2. 1 + 2 is 3. 2 + 3 is 5. 3 + 5 is 8. 5 + 8 is 13. 8 + 13 is 21. 13 + 21. This is the Fibonacci sequence. Yeah. The Fibonacci sequence is to get each term, add the previous two. So 1 + 1 is equal to 2. 1 + 2 is 3. 2 + 3 is 5. 3 + 5 is 8.
Add the last two.
Add the previous two, yeah, to get that one. Now, this is, I'm not a biologist, but there's a whole bunch of applications in biology. I don't know if Mr. Curry, it's Mr. Curry has told you this yet, right? But like, basically, as things grow, it'll be like the number of flowers, number of petals on a flower follows the Fibonacci sequence. The number of like leaves on a pine cone follows that sequence. There's a whole bunch of real life applications that actually works that way. Okay, letter E. Someone new, please. Sorry, you're out. Somebody new. Go.
It's 25, 36, 49, 64.
Yeah, how'd you get that?
It's odd numbers.
Okay, now this is the interesting part. It is. So what? There's two ways to get this. So this is +3, +5, +7, +9, +11, +13, +15. So they say adding odd numbers. Now, when I made up this sequence, I'm a math teacher, so I didn't actually add odd numbers. Can anyone think what me as a math teacher might have done here? Because that's still right. Nice and what sequences, there's 10 ways to get them. Joe, what do you think me as a math teacher did for this? Yeah, that's what I was using, right? 1 squared is 1, 2 squared is 2, 3 squared is 9, 4 squared is 16, 25, 36, and so on. And that's the thing with these, there's not always one right answer, but as long as it works. Like for this one here, you can get all sorts of interesting ones. That's why it's showing up data, so it actually worked out. And now letter F, this is my joke. Anyone seen those 6 numbers before? Anyone get a paddle for that? You guys, this is too old. This is me dating myself. These are the lost numbers. And actually, Lost is a show that like has a huge cult following. I don't want to say nerdy following, but I will say a nerdy following. And they have mathematicians analyze the, what out of those numbers, trying to get a sequence out of them, and there is no actual sequence. There's just 6. Like, what would the next number be? There's no mathematical pattern to that they could something like that. And if you've seen Lost, people went crazy. Like, you guys are too young on that, but when Lost first came out, it was. Yeah. So that ending was bad. Okay, I'm going to stop that right there before I go on to my next one here. Where's my recording that? Yes, it was. Okay.